We've already met the relative humidity, which is the ratio of the mass of vapour over the mass of dry air. We can now also define the specific humidity, which is the ratio of the mass of water vapour to the mass of moist air. And the mass of moist air is equal to the mass of the dry air plus the mass of the vapour. As a non-dimensionless number, that would be measured in kilograms per kilogram. But as done for the relative humidity, it's more convenient, given the smallness of the values, and to do it on a SQT log P aerological diagram, to calculate the specific humidity QV as the mass of vapour in grams divided through by the mass of moist air in kilograms. And this is used for very precise computations, though for synoptic forecasting purposes the mixing ratio is sufficient. So let's show that. The specific humidity is going to be the mass of the vapour divided through by the total mass, the mass of the vapour plus the mass of the dry air. If we divide through numerator and denominator by the mass of the dry air, then the numerator we have R, and on the denominator we have 1 plus R. And so we can calculate QV very easily off the SQT log P aerological diagram. So consider, for example, a mixing ratio of 20 grams per kilogram. The unit value of unity in the denominator is going to be 1,000. That's 1,000 grams per kilogram. And so QV, the specific humidity, is 20 over 1,000 plus 20, which is 0.0196 kilograms per kilogram. And the mixing ratio is 0.02 kilograms per kilogram. And so we can see that the specific humidity Q is approximately equal to R, the mixing ratio, within about 4% for most meteorological purposes. So you could measure the specific humidity very easily off a SQT log P aerological diagram by simply measuring the mixing ratio.